Well, it's a great honor to be here today, and I'd like to thank Kyoto University and the Inamori Foundation for this very special invitation to talk. I guess humankind has been trying to forecast weather since the dawn of civilization. But it's only since the very early 20th century that it was proposed by Norwegian meteorologist Wilhelm Bjerknes to try to forecast the weather using the principles of science. That is to say, to take an estimate of the current state of the atmosphere obtained from observations and to evolve that state forward using the laws of physics. Now, by laws of physics, perhaps the most important law of physics in meteorology is Newton's second law of motion. I guess many people know from high school force equals mass times acceleration, the famous law of Isaac Newton. The particular form of Newton's second law that is used in meteorology and oceanography is called the Navier-Stokes equations. Now, you do not have to be a mathematician. I will not try to explain this equation in detail. But with just 23 mathematical symbols, we are able to describe circulations in the atmosphere from the very largest weather scales, thousands and thousands of kilometers across, to the very smallest gusts of air, or the air coming out of my mouth. These are all described by this single equation. And so for me, as a scientist, I like to think of this equation as something with much beauty. And for me, it is a work of art. And perhaps I can relate it to, for example, this very beautiful and famous Japanese work of art. But actually, I'm not going to do this. I'm instead going to relate this equation to a rather different work of art, a Russian doll. But this is a very special Russian doll. This special Russian doll unpacks not into 4 Russian dolls, or indeed 8 Russian dolls, or 12 Russian dolls, or 16 Russian dolls. It unpacks into billions, in fact trillions, of Russian dolls. And the reason for equating this Navier-Stokes equation to this Russian doll is that if we want to solve this beautiful equation, we also have to unpack it. To solve it on a computer, we have to unpack it. And it also unpacks into trillions of individual equations. And this makes it extremely difficult to solve. And in fact, the only way to solve this equation is to use powerful electronic computers. So, for example, the largest Russian doll represents a large-scale weather system, like a tropical cyclone. Smaller Russian dolls might represent individual cloud systems. And maybe smaller Russian dolls still represent small gusts of air. But the problem is, even the very biggest computers in the world today are not big enough to represent all the Russian dolls, all of the scales of motion. So what we have to do is start throwing away Russian dolls, truncating our equations. So here I'm throwing away Russian dolls, throwing away the small Russian dolls, and then I stop when my computers are big enough to solve the equations for the remaining Russian dolls. And a typical weather forecasting model, or even climate model, can represent scales of motion from the very, very largest scales on the planet down to about, say, 25 kilometers. Now, there are many, yes, so I can represent large-scale cyclones, weather cyclones, but individual clouds are still too small to be represented explicitly. So what I have to do now is find a simplified way of representing all of the scales that cannot be resolved explicitly. So this block of wood, so this is not so much a work of art compared to the Russian doll. It is rather crude. And indeed, the representation of all of the scales, the cloud scales and turbulent scales that I cannot resolve, are also represented by rather crude, simplified, deterministic formulae. They're called, in my work, we call these parametrizations. They're simplified equations to describe processes that the climate models can't resolve. So this is a fundamental reason why simulating weather and climate is still approximate, it's not precise. And this is how the Navier-Stokes equations are represented on a computer. The first attempt to forecast weather by electronic computer was made by a team at Princeton University in 1950. And the team was actually led by John von Neumann. Von Neumann is a very famous mathematician who actually was mentioned yesterday. He did much pioneering work in mathematics and quantum physics. But he also realized that one of the applications of the evolving electronic computers was weather prediction. Well, the science of weather prediction has evolved gradually and steadily. And in 2015, a review paper was written in Nature, which described the evolution of weather forecasting since 1950. And it has evolved slowly as computers get bigger, as satellite data provides new observations, better observations, more complete observations, and also as our scientific understanding has improved. So the skill of weather forecasting has improved. But as the title says, it's been a quiet revolution. Nothing sudden, but gradual evolution. And today, we can typically make accurate forecasts over 1 week ahead, as I will show. However, there is a problem. There is a problem with this paradigm of Bjerknes, that all you need to do is take observations to create the initial state and then use the laws of physics to create the forecast state. There is a problem. And the problem can be illustrated this way. So what I want to talk about is a weather event which occurred almost 30 years ago in the UK. And it is perhaps the single most famous weather event, certainly to have happened in southern England. Everybody who is old enough will remember this weather event. What I'm showing here are two weather maps, maybe 2 days before this weather event occurred. These two weather maps are almost identical. There are very, very, very small differences, but they're really too small to see. And what I'm going to do is take a weather forecasting model and evolve both of these states forward in time by roughly 2 days, just over 2 days. I can get this to work. Here we go. So my weather forecast model is evolving this forward into the future. And we're going to stop on the day where this very famous weather event occurred. Now, the top weather map, if you are familiar with, this is surface pressure, you will know that this would be quite a nice day in England, certainly in southern England. There's very little pressure gradient, maybe a nice day for an outdoor picnic. But this weather map, on the other hand, shows a very intense low pressure, a vortex, with extremely strong winds on the southern edge. Now, this man is the BBC television weather forecaster, and his job is to tell the public what the weather will be based on the forecast made by the Met Office. And in those days, there was just one single forecast made every day, roughly, or every 12 hours. And essentially, this is the forecast that he received from the Met Office. So he predicted it will be a nice day. Weather tomorrow should be okay. What happened was the worst storm to hit England, southern England at least, in many hundreds of years. And people couldn't understand how bad he could have been with his forecast. So what's going on? Well, we can understand what's going on with a rather simpler model that was discovered, in fact, by MIT meteorologist Ed Lorenz, who won the Kyoto Prize in 1991 for this work. He realized that, first of all, the weather can be unpredictable, but he realized also that one can illustrate mathematically this unpredictability with just 3 Russian dolls. This was a complete surprise. Everybody assumed that unpredictability was the result of having millions or billions of Russian dolls. But he showed no, just with 3 Russian dolls. So this means 3 equations in 3 variables, capital X, capital Y, and capital Z. And I can illustrate this unpredictability in Lorenz's model with this illustration. So what we have are 2 curves. One is red and one is blue. And they start off with virtually identical initial conditions. The most smallest perturbation has been added. And for a long time, they track together, but then they completely diverge. And let's say this one might have been the nice weather, and this one the stormy weather. So this phenomenon is called chaos. You've probably heard about it. It's very famous. And in fact, the principles of chaos have been applied in many areas of science: physics, biology, social science, economics. It's been almost universal. Now, you may think from chaos that it's impossible to predict the weather, let's say, more than 2 days ahead. But I've already told you that we can routinely predict over a week ahead very accurately. So how can we understand this? So I'm going to continue with Lorenz's model and show you some forecasts, if you like, from different initial states. But this time, what I'm going to do is not run a single forecast, but an ensemble of roughly 100 forecasts from almost the same initial state, but not quite. So I introduce these tiny perturbations. And what you see is, from some initial conditions, there is very little growth. There's very little divergence of the individual trajectories. So this would be very predictable. On the other hand, down here, we can see there is this rapid growth of the trajectories, and this would be extremely unpredictable. And this one here sits somewhere in the middle. And it turns out in Lorenz's system, and I didn't explain, this shaded figure is a special type of geometry that Lorenz discovered, fractal. It's called fractal type of geometry, where the system resides in the space of the variables x, y, and z. And it's only in some small parts of this geometry down here where you get this strong unpredictability. And this is typical, that in a chaotic system, the degree of predictability depends on the starting conditions. Very predictable starting conditions, let's say semi-predictable starting conditions, very unpredictable starting conditions. So let's imagine if one could actually forecast predictability ahead of time, how useful this would be for society. We'd be able to know when we were in a situation where we would have little confidence in the details of the weather, and on other occasions we may be very confident. We would know with great confidence about the details of the weather. And this is something I've been doing maybe for the last 30 years or more, trying to develop this ensemble forecasting technique and take it from this simple scenario into a realistic world of operational weather and climate prediction. So, for example, we've been able to retrospectively run the October 1987 storm in this ensemble framework. So this was something we did just a few years ago, something that wasn't possible at the time, but is possible now. So here are 50 forecasts. This is the UK here, and this is a surface pressure map. But 50 forecasts from, again, almost but not quite identical starting conditions. And what you see is there's a very, very, very large spread in the forecasts. So some forecasts have this intense low pressure system in different places. Other forecasts have no low pressure at all, in fact, little ridge of high pressure. So this is telling us this indeed is a situation where no forecaster, even today, would be able to make a deterministic, a definite prediction with any confidence. So how would you present this today? How would a modern weather forecaster present this today? Well, what you could do is you could count the number of ensemble members that, for example, had hurricane force wind gusts. And since there are 50, if we multiply that number by 2, we get, roughly speaking, a probability of hurricane force winds. So this is a map showing the probability of hurricane force wind gusts from this ensemble forecast. And it shows that across the English Channel and into southern England, the probability was around maybe 30% or even 40% in some places. Now, normally, hurricanes don't happen in England, so 40% probability is extremely high, extremely large number compared to the normal probability, which is 0.000001% or something. So this is potentially very important information, even if we cannot say precisely. It can warn people there is a substantial risk. And this is the important word I want to stress in the rest of my talk, risk of extremely damaging situation. And I would say in the last decade or so, ensemble forecasting has really become widely used around the world, and it's transformed weather and climate prediction. And it really, the fact that we can now make probability forecasts in a quantitative way, it means we have now a reliable tool for objective decision-making that we never had with the old-fashioned deterministic predictions. So I want to give 3 examples of an ensemble forecast, basically from the organization where I worked for many years, the European Centre for Medium-Range Weather Forecasts. And the first one is Hurricane Sandy, which you will remember hit New York. And this is the ensemble forecast of the tracks of Hurricane Sandy over a week before it hit New York. And this is when it was down in the Caribbean. Now you can see a number of members of the ensemble track across the Atlantic like a normal hurricane does. And indeed, at the time, many of the operational weather forecasts around the world also were predicting, the deterministic forecasts were predicting that it would track across the Atlantic. But the ensemble indicates there is a very substantial probability of it recurving and hitting the east coast of the US. So at this range already, well over a week before, we can give a warning of the risk of a storm hitting somewhere on the east coast. We don't know exactly where at this stage. But like in Lorenz's example, not all hurricanes are unpredictable in this way. This is Typhoon Haiyan, which hit the Philippines, a record-breaking tropical cyclone in the Pacific, that actually the tracks of which, these colors represent probability, the probability of the track of the hurricane or the tropical cyclone passing through a particular location. And this actually was extremely predictable, even 10 days ahead. And I'm going to come back to this example in a minute. And then just finally, I want to say that ensemble forecasting can also be used on longer timescales. And at the European Centre for Medium-Range Forecasts, we also do predictions 6 months ahead, and in particular of things like the El Niño phenomenon, which is a warming in the Pacific Ocean. So this actually is fairly much the latest prediction of the El Niño state for, say, the end of this year, December 2017. And this is 0 is the normal sea temperature. So this is a prediction of sea temperature. It's an ocean. This is done with a coupled ocean atmosphere model. And there's actually a lot of uncertainty, as you can see. But there's a slightly higher probability of the sea temperatures actually being warmer. So we're being in a weak El Niño by the end of the year, and a smaller probability of cooling. And there are implications for this that I'll talk about shortly. I just write a couple of just put up a couple of papers of my own. So I started to work on this at the UK, United Kingdom Met Office, and our first ensemble forecasts were back in 1985. And then we implemented at the European Centre the operational ensemble system, which probably is, well, we'll come onto it, is probably the most skillful in the world at the moment, in 1992. And then in the 1990s, I worked on the seasonal forecasting system, again in a European context. This paper here, I just want to very briefly flag it up because it introduces a kind of a paradigm shift in the way we formulate weather models. I want to return to the Russian dolls, and here we have I've replaced I've changed the block of wood by a fuzzy block of wood. And this is because it's important in an ensemble forecasting system to represent the uncertainty of the model itself. Nature, by the way, agrees. We have to represent the uncertainty in the model. And we do this through a process called stochastic parametrization. And this basically means replacing these deterministic formulae by probability distributions. So the model itself is now partially probabilistic. And this has been a change, if you like, in the philosophy of developing models. As I say, many centers now, most centers, in fact, I think all operational centers in the world run ensemble forecasting systems. And the United Nations World Meteorological Organization has charged the Japanese Meteorological Agency to actually be the lead center on the verification of these ensemble systems. So this is one of their products comparing the skill of different operational ensemble prediction systems around the world. Okay, I've talked a bit about the basic science of ensemble forecasting. I want to now talk about some of the societal impacts, the importance of this for societal decision-making. I guess in the last talk we heard about Sendai, but Sendai was also the place where the United Nations Third World Conference on Disaster Risk Reduction was held back in 2015. And they produced a very important document called the Sendai Framework for Disaster Risk Reduction. And it sets out some objectives that society worldwide should have in disaster risk reduction. And one of the objectives is to substantially reduce disaster mortality, deaths from natural disasters, by 2030. But how will we do that? Now, the first thing I want to say is, according to the United Nations Office for Disaster Risk Reduction, 90% of disasters are weather-related. There are obviously earthquake-related disasters as well, and these are important, but most of the disasters are actually weather-related. One such disaster was indeed Typhoon Haiyan, affected almost 12 million people, 2.5 million needing food aid, 500,000 displaced, and so on. But there was a lot of criticism of the international disaster relief agencies after the typhoon had hit. This is from the BBC News at the time in 2013. Two senior UN officials visited Tacloban and identified an urgent need for transport, for emergency shelter material, for hygiene kits, for body bags, for establishment of family tracing services. A lack of trucks and a lack of fuel shortage is severely hampering the response. And here we see people holding up signs, we need help, we need food, we need water. And part of this has come because the aid agencies are responding to the disaster. They are meeting the needs after the disaster has hit. They're reacting to the disaster. Whereas now, we're beginning to get the tools we need to be able to act ahead of time, to be proactive rather than reactive. To be proactive, the disaster agencies need some quantitative estimate of the risk of these disasters. And with ensemble forecasting, we can now provide this estimate of risk and give the international community the tools to decide when to get emergency aid into place before the event strikes, not after the event strikes, and hopefully avoid all these problems that occurred. I just want to give you a simple example of how one does this. So this is very standard decision theoretic analysis. Suppose we represent the loss or the damage caused by some extreme weather event, E, by this symbol L. This could be in pounds or euros or dollars or yen, some amount of money associated with the loss or damage, if no precautionary action is taken. And let me call the symbol C the cost of taking precautionary or proactive action, the cost of sending the aeroplanes out to the likely sites where the disaster will occur, and providing the emergency tents and the emergency food and the emergency water ahead of time. So that's the cost C. Finally, suppose we now have a probabilistic estimate of the likelihood that the event will occur, P. So this can be obtained from an ensemble forecast. Then this would be a simple formula for deciding whether or not to take precautionary or preventative action if the probability times the loss is greater than the cost. Economists often call this product of P times L the risk. So if the risk exceeds the cost, take action. So if the probability is large enough, or if the loss is large enough, or if the cost is cheap enough, then take action. And with ensemble forecasting, we now have that final quantity P that we need to be able to make that kind of decision. Let me give a couple of examples. This is a case in India, Uttarakhand state, where in 2013 an intense rain event occurred. This was studied in detail by a colleague of mine, Professor Peter Webster, from the Georgia Institute of Technology. Traditional deterministic forecasting techniques failed to warn of the impending deluge, and over 6,000 people were drowned, together with large infrastructure destruction. This shows contours of forecast probability of the intense flooding event at different lead times, so different number of days before the event occurred, from the European Centre for Medium-Range Weather Forecast Ensemble. So let's imagine how one could use this information based on this formula. So 7 days before the event occurred, the ensemble was predicting this contour is about 50% probability. So about 50% probability. So this is a large enough number that maybe if you were in charge of the emergency response, you would want to at least get prepared for a possible disaster, even though you may not yet deploy your resources. By 4 days before the event, that probability has reached now 80%. So this is now probably a large enough number that you would want to start to get disaster relief into place. And 1 day ahead, the probability has risen to over 90%, so this would be time to get final preparations in place. So this is just an example of a real occasion, of a real event, where probabilistic forecasting can give you the numbers you need to make these decisions. But it's not only about the international emergency response, it's also about local action. And I was involved with a project, again with Professor Peter Webster from the Georgia Institute of Technology, on looking at probabilistic forecasts of flooding of the Ganges and Brahmaputra, mainly for Bangladesh. And Peter and his colleagues actually went out into the field, into villages, and educated local people about probabilistic forecasts of flooding. If you have several days of advance warning, you can do things like moving your livestock to higher ground, or you can harvest crops early. These sorts of things cannot be done with just 6 hours warning, but they can be done with several days warning. And the question, again, is how high the probability has to be before that action can be taken. But that's a decision that can be made. I hope we don't have flooding here. That's a decision that can be made by local people. And in fact, what was shown was that local people can understand this notion of probability. It's not, people often say, oh, the public don't understand probability. They do. And in the villages in Bangladesh, for example, the imam at the daily prayer time would transmit this information about the risk of flooding. And this is some words from the imam in the local village. We disseminate the forecast information to understand the risk during prayer time. He said, I myself use the flood forecast for saving information, for saving crops, making decisions for seedling and transplantation, and saving household assets. And in the pilot project, it was estimated that the savings of these warnings exceeded the typical annual income of the villagers. And just finally, I want to say that it's not just about short-range or weekly weather forecasting. I mentioned the El Niño forecasts. And when an El Niño event occurs, there are certain implications, particularly around the tropical belt. One of the things that we studied in the paper that I mentioned earlier was about the link between El Niño, rainfall in Africa, and the occurrence of epidemic malaria in parts of Africa. So in countries, for example, like Botswana, malaria occurs episodically. And when it occurs, there can be these epidemic outbreaks. And it's very strongly linked to weather, the seasonal weather. And the seasonal rainfall is in turn linked to the El Nino in the Pacific Ocean. So basically, we were able to make probabilistic forecasts of, this is with work, I should say, with the University of Liverpool School of Tropical Medicine and the International Research Institute for Climate and Society in Columbia University in the US. We were able to make probabilistic forecasts of malaria incidents, the probability of epidemic malaria occurring in particular regions of Africa, a season ahead now, not just days, a season ahead of time. Now, with that information, again, the aid agencies can send bed nets to affect the likely affected areas or spray stagnant water prior to the rainy season, kill the mosquito larvae. But it's something one can only do if you have a few months of lead time. So this is an example, one of the many examples of how seasonal risk prediction can be extremely helpful for society. So I've got 3 minutes to finish, and I just want to spend those last 3 minutes talking about the final part of this diagram, the link to technological advances. Looking to the future, one of the most important things we must do in my profession is develop models that can, where the Russian dolls extend right down to cloud scales, to 1 kilometer. They currently stop around, say, 20 kilometers. We've got to get them down to 1 kilometer. Then we will be representing these cloud systems with the Navier-Stokes equations and not these simplified parameterizations. This is extremely important for improving both weather and climate prediction. But this will require next-generation supercomputers. And there's currently a big race around the world to develop what's called the exascale supercomputer. So this is from a Greek word, exascale, meaning that one can perform 10 to the power 18 numerical computations per second. So a million calculations per second. Sounds fantastically large, but this is what is needed to be able to develop these cloud resolve models. So Japan is certainly right in the forefront of research. Tokyo Institute of Technology in Riken, developing Japanese supercomputers for exascale. In the European Union, they're putting a lot of funding into exascale computing. Currently, China has the world's fastest supercomputer, but it says here the US wants to change that. So again, the US is putting lots of money into exascale computing. But there is a problem here, and this was actually identified in this morning's talks, and that is what is constraining, what is preventing us reaching this exascale computing is the amount of energy or power that is needed to run these machines. It's power that is the constraint. They're using too much power. This is a quote from the head of a US supercomputer center. Hitting exascale compute levels requires a fundamental rethink of virtually the entire computation process. One of the biggest problems standing in our way is power. Not just the power required to run a task on a CPU, a processor, but the power required to share that data inside the computer. Now, partly this problem will be solved with new types of materials that we heard about this morning, so this is an important aspect. But it's also important for software designers to look again at their code and see if they can make them more energy efficient. And this is something that is very much a focus of the research in my group in Oxford, and we have a new grant for 5 years from the European Union to do this work. And I want to describe it very briefly in the last, I'm running out of time, but just the last minute. In computing language, we call a bit is a binary digit, which is either a 0 or a 1. It's the essential quantum of computing, 0 or 1. And in conventional scientific computing, across pretty much the whole of science, the default is that every variable, let's say here a Russian doll, is represented with 64 bits. Now, if we have a billion Russian dolls, then we have 64 billion bits which are being moved. And this takes up a lot of energy to do that. What we're looking at is, and it's been motivated by the fact that the parameterizations are now stochastic. They have some randomness in them. We're looking at whether we can reduce significantly the precision of these variables, reducing the precision as we go to smaller and smaller variables. So we're currently wasting computer resources representing all variables by 64 bits, and there are considerable energy savings to be had by only representing the bits that contain real information. So our research is trying to quantify, as a function of scale, how many real bits of information are there. And the plan is then to reinvest the savings in energy to increase model resolution. So I wrote about this in Nature a couple of years ago, that we need to think about imprecision as a route to supercomputing in the future. I think there's a lot more I could say about this, but I think I'll move over that. So I'm just going to finish with my last slide summary. Before the development of ensemble techniques, deterministic forecasts were really unreliable tools for decision making. The example with the October storm is a good example. It's unreliable. But ensemble forecasting is now beginning to revolutionize decision making. I talked about disaster relief, but there are many areas: food security, health, transport, energy, financial. There are many financial decisions as well. It's an essential tool to make society more resilient to extremes of weather and help us meet the Sendai framework goals. And I should say, I haven't spoken at all about climate change, but all the projections of climate change are indicating that extreme weather is becoming more likely. So that the ability to be able to predict risk of extreme weather is becoming more and more important, and will become more and more important in the future with climate change. And finally, this work is really a key application for exascale computers. But more than that, it's a key application for helping the designers of exascale computers to design energy-efficient next-generation computers. And I'm very excited about this potential synergy, which incidentally might have applications in other fields as well, such as astronomy, astrophysics, turbulence in plasmas, and other multi-scale systems. And that's my talk. Thank you very much.